We are in chapter 8, section 8.4, and we are dealing with matrix transformations from Rn to Rm. So typically we are working with finite dimensional linear spaces. And what we want to see is what happens when we have different bases for the inputs and outputs, for the input space and output space. And how does that affect the representation matrix? So each time we change basis for one of the linear spaces, we will get a different representation matrix. So what we want to see is how to do all this. So we are given a linear transformation from linear space V to linear space W, and obviously there's a basis for a linear space V called BV, for instance, and we also have a basis for the linear space W, BW. And what we want is to learn how to build the representation matrix relative to bases BV and BW. So this is the notation. We are going to say, okay, this is linear transformation. So with these brackets, this is a representation matrix of a linear transformation T relative to bases BV and BW. Okay, so that's what we are looking for to learn to build. Now, once we have this representation matrix, we need to know how to use it. So we are going to see how to use this representation matrix to actually find image of a certain object or a vector under the action of the linear transformation T. So both of these pieces are quite easy and straightforward. There are some computations involved, so we are just going to see how to do things, and actually it's going to be very easy and straightforward. The important thing to remember is that our linear transformation works on objects. So it takes an object from V and then does something to it, and as a result, as the image, we get an object living in W. So linear transformation works on objects. Whereas the representation matrix for that same linear transformation, the representation matrix works on coordinates of objects. So this is what is important to remember in this entire course here related to the section 8.4, is that the matrix representation works on coordinates of objects, whereas linear transformation works on objects themselves. Okay, so each time we change a basis for one of the linear spaces, our representation matrix changes, but it's the same linear transformation T. Linear transformation doesn't change, but its representation matrix changes depending on the basis we choose for the domain or the codomain. So you see the notation here. We have representation matrix of the linear transformation T relative to the basis of domain BV and the basis of the codomain BW. So this is the notation and this is the order. In the book, they swap this order for some weird reason. So you need to be smart and use something that is quite intuitive. The first letter will denote the basis for the domain, and the second letter is basis for the codomain. Just keep it simple. As we know, just a reminder that the transformation transforms objects from the linear space V into objects living in the linear space W. So V is domain and W is codomain. You can also say, okay, V is space of the inputs for our transformation, and W is space for the outputs. That's where the outputs live. If you look at the transformation T as if it was some type of transportation vehicle, then you can say that the V, so your domain, is like a departure space, and W, the codomain, is like an arrival space. So you have your linear transformation that takes objects here, transforms them, and brings them into W. So it's like transforming them and transporting them from one space to another. Now if we deal with linear transformations, linear transformation is just a transformation that again transforms objects from linear space V into objects in linear space W, and it satisfies the two linearity conditions. Those are the two linearity conditions that are important. We know that when V and W are finite dimensional spaces, and we are going to work only with those spaces, in that case we have the representation matrix that can be associated with the linear transformation. So that's what we are going to explore. Again, this is super important to remember that linear transformation works on objects. So if we have a linear transformation from Rn to Rm, so those are vectors. As input, I have a vector V in Rn, and then I apply the linear transformation T, and I get the image of the vector V under action of linear transformation T. So the image is T of V. That image is again a vector that lives in Rm. So linear transformations work on objects. In this case, because we are working on linear spaces Rn and Rm, the objects in question are the vectors. Now I stress on the word object because here you have a linear transformation that takes matrices 2 by 2 and does something to them and transforms them into real numbers. So this is what happens. Let's say this is a linear transformation that takes a matrix 2 by 2 with components A, B, C, D, and associates to this matrix a real number that is actually just summation of the coordinates. So this is a linear transformation that has as domain linear space of matrices 2 by 2, and codomain is real numbers. So it is taking as object matrix 2 by 2, and it turns as result another object which is a real number in this case. So be careful, that's what it means. Object is just things that are not necessarily vectors. We will spend most of our time working with vectors, but all this theory is applied to many other linear spaces. So another example is if I have a linear transformation working on polynomials of degree n, and then doing something to them and transforming them into real numbers. So for instance, this linear transformation will simply add the coefficients for a polynomial of degree n. Okay, so it takes as an input polynomial of degree n, as output you get another object which is a real number. So you have one type of object as input and another type of object as output. In this example here, you have a linear transformation transforming objects which are vectors in R2 into other objects which are vectors in R3. And this is a linear transformation in question. This is an example. Here is another one where we take as domain polynomials of degree 3. So polynomial of degree 3, this is general polynomial of degree 3. And we transform them by a linear transformation into a matrix 2 by 2. So we are taking an object which is a polynomial of degree 3 and transforming it into another object which is a matrix 2 by 2 in this case. So we simply just assign the entries of the matrix in this order which are correlated with the coefficients of the polynomial. So this is very important to understand that linear transformation works on objects, and objects can be different. That can be columns of vectors, columns of numbers like vectors, could be matrices, polynomials, real numbers, and other stuff. We already know that differentiation and integral are also linear transformations. So you're transforming functions into other functions. So be careful about that. We are going to work mostly with vectors, but this theory is applied to many different types of objects. And this will be very important later on, because these objects here, let's say in this example, these are vectors with 2 components, and this is as output we get a vector with 3 components. Okay. Opposed to that, we have a representation matrix for a linear transformation. A representation matrix works on coordinates of objects. It doesn't work on objects themselves, it works on coordinates. Obviously, those coordinates are related to a basis chosen for a linear space. Okay? So, when we choose standard basis for the domain and codomain, we have a standard matrix. We already know how to compute this standard matrix. But if we choose different bases that are not necessarily standard for domain or codomain, then we have a different representation matrix that will change related to a basis. So each time you change a basis, this representation matrix will change, and that's why we need to specify the basis for domain and codomain that we use to obtain this representation matrix. This will be very important. So first one is for the domain, the second one is for the codomain. So this representation matrix works on coordinates of objects, which means when you multiply this matrix by a vector, you will multiply by a coordinate vector relative to basis BV. We will see how to do all this. But what really matters is to remember that representation matrix works on coordinates of objects, whereas the linear transformation itself works on objects themselves. A very important note, when we are working with polynomials, with the vectors. When we are working with the vectors in Rn, if we take a standard basis, so the standard basis of Rn, we know already that the coordinates of a vector in standard basis of Rn are equal to the entries of the vector itself. That's straightforward. So I have a vector in Rn, so these are the components or the entries of the vector, and we know that the coordinates of the same vector in standard basis of Rn are actually the entries of the vector itself. So these two things, we can say they are equal, even though they represent different things, because this is a vector and this is another representation or a list of coordinates of a vector in standard basis, but those two are equal. Okay, so this is good for vectors, okay, and we are going to use this massively. And this is only good for standard basis of Rn. So how do we build a representation matrix? So this is a procedure. So we have our linear transformation T that goes from V to W. So we have a basis for a linear space V, which is basis for the domain. So basis B with vectors V1, V2, Vn. And we have a basis C for the domain W, and this basis is formed by vectors W1, W2, W3, Wk. So these two linear spaces don't have necessarily the same dimension, that can have different dimensions completely. So that's why I chose different subscripts here. So how do we build the representation matrix? So these are the steps, and they are classic steps to apply every time. First thing, we will apply the linear transformation to the basis vectors of the domain. So to the basis vectors v1, v2, v3, vn. We just do that. This gives us the images t of v1, t of v2, t of vn. And these images are expressed in the standard basis of the codomain, which means these are the vectors themselves, or objects themselves. Now the second step will be to find the coordinates of the image, so t, v1, t, v2, t, vn. So we need to find their coordinates in the basis C of the codomain. So this part requires a little bit more work because we need to solve a linear system using Gauss-Jordan. So once we do that, we will get the coordinates of the image in basis C. Now we take those coordinates and we just put them into columns of a matrix. And that's how we build the representation matrix. So representation matrix of the linear transformation T relative to the basis B of the inputs and basis C of the outputs is given by this matrix. We just take these coordinates in basis C of each of the basis vectors from the basis V, B, and we put them in the columns. Tuck, tuck, tuck. So this notation simply says that the input space, the basis was B, and the output space, the basis was C. So what I have in the columns here are the coordinates in basis C of the image of the basis vectors from the domain. So now I'll repeat this message 1,000 times because it's very important. Representation matrix works on coordinates of objects. So if I have linear space Rn and I have two bases, one is the standard basis and another one is some different basis, B, then a given vector from Rn, we have its coordinates in the standard basis are simply the components of the vector itself, because this is how the vector is decomposed, obviously. Now, if I decompose this vector and express it as a linear combination of basis vectors from basis B, I will get different coefficients, obviously. So these coefficients, they are the coordinates of the vector V in the basis B. So these are things we already know, but it is good to remind ourselves. So now, if I apply the linear transformation to the vector V in question, when I express it in the standard basis, this is what I get, and then I apply the linearity of the linear transformation and I get this. So basically, the standard matrix, we already learned that is simply built by the column vectors, which are the image of each standard vector, so from standard basis, under the action of linear transformation T. So this is something that is straightforward. We did that already. So this is our standard matrix, and you see we multiply it by the standard coordinates, which is the same as multiplying by the vector itself, and that's how we get the image. So that was straightforward. Now, similarly, when we express vector V in a basis B, so we express it as a linear combination of basis vectors from the basis B. So this is what we get, obviously. And then we apply again linearity of the linear transformation, and we get this part here. So what is this? This is a linear combination of images under the action of linear transformation T, images of each basis vector from basis B. So image of B1, image of B2, image of Bn. So we get this linear combination here. That means that representation matrix relative to the basis B for inputs and standard basis for outputs, because these TB, these are vectors and they are expressed in the standard basis, obviously. So to build this matrix, it's simple. I just put these images of the basis vectors in the columns, in the correct order, obviously. So it's very straightforward. So the notation for the representation matrix, when I have standard matrix, so that means the domain, for the domain I use standard basis, and for the codomain I use standard basis. It's simply image of each basis vectors from the standard basis, and I put them in order in columns, and that's what I call the standard matrix, TSS. Now if I use a different basis for input space for the domain, if I use basis B, then in the columns I'll have the image of each basis vectors from basis B under the action of the linear transformation T. So basically I apply T, linear transformation T, to each basis vector from basis B, and I put the results in corresponding columns. So what I get is a representation matrix relative to the basis B for the domain and standard basis for the codomain. Now we can complicate things a little bit, so I copied this from previous slide just to make the contrast here. If I am building a representation matrix relative to basis B for the domain and some basis C for the codomain, so C is not a standard, it's a different basis. So what do I do? Similarly, I need to apply T to the basis B as I did here. But now my outputs, I need them in the coordinates of basis C. So I need to take each single one of these and find its coordinates in basis C. So that's what I have here. So this is a list of a vector containing the coordinates of TB1 in basis C. Okay? So this requires work. I need to solve the linear system. And then I need to solve another linear system for TB2. So I have the image of the basis vector B2, fine. Now I need to find its coordinates in basis C. Good luck, that's a work. And then I put the result in column 2, and I go further and further. So this part will require a little bit more work. It's easy to apply a linear transformation to each basis vector, whatever the basis is. It's not a big deal. But if your basis for the codomain is not standard, like here it's C, that means now it's not over. You need to express each single one of these vectors that you got. You need to find their coordinates in basis C. Good luck, it's long. So this is what it means when I write representation matrix of a linear transformation T relative to basis BC. It means that I apply T to each basis vector from basis B, and then I need to find the coordinates of the image in basis C. So, and then I put the results in columns of the matrix. So that's my representation matrix relative to basis B and C. So now I repeat the same thing again, just to make sure that you understand what's going on. Again, representation matrix will work on coordinates, and that's why I need to be careful here. So if I build a standard matrix, in the standard matrix the columns are just images under T of each basis vector from standard basis of the input space, and the results are the vectors here, vectors in R M. So the vector and its coordinates in the standard basis is the same. So that's what I put simply the image here. So my standard matrix relative to standard basis for inputs and standard basis for outputs is simply the matrix where each column is the image of basis vector, standard basis vector from Rn. Now, if I want to build a representation matrix relative to basis B for the inputs Rn and the standard basis for outputs Rm, it's not a big deal. I just take the vectors from the basis B and I apply the linear transformation to them, and I put the results in columns of the matrix, because TB1 is the vector in Rm, and that vector from Rm has the same components as its coordinates in the standard basis. Is the same thing. So I just put them here. So that means my inputs, the coordinates are in basis B, and the outputs are in standard basis. If I make things more complicated, and I have a representation matrix for the linear transformation T, but relative to basis B for the inputs and some basis C for outputs, then I need to take each of the images, so TB1, and I need to find its coordinates in basis C and put it in the first column. Take TB2, the vector, and then find its coordinates in basis C and then put it in the second column, and so on. So this part here is a little bit heavier because we need to solve a huge linear system using Gauss-Jordan. So here the inputs are given in coordinates of basis B and the outputs are given in the coordinates of basis C. A representation matrix works on coordinates of objects. That's what it means. Obviously, I can take a standard basis for the inputs and still have some weird basis C for the outputs. It's not a big deal. I take the image of each standard basis vector and I find its coordinates in basis C and I put the results in respective columns. Again, representation matrix works on coordinates of objects. One important remark here, you need to be careful when you have a linear transformation from Rn to Rn. So the same space in the input and the output. Okay? When you choose a basis for Rn, let's say basis B, whatever the basis B is. Well, it's the basis for Rn for the inputs and for the outputs, obviously. Okay, you cannot have one basis for the input space and this output space is the same space, but then you have a different basis. That makes no sense. So when you have the input space and the output space, the same space, in this case Rn, when you pick a basis for Rn, it's a basis for the inputs and for the outputs. Okay, be careful. So here, you need to remember that a linear transformation T works on objects, which means it takes a vector from Rn and then it gives an output vector from Rn, a vector. Okay? So when you compute the representation matrix for T relative to basis B, that means you have basis B for inputs and basis B for outputs, which means you apply the linear transformation T to the basis vectors from basis B. So TB1, that's easy. TB2, TB4, TB5, TBn, fine, good. But the job is not over. Now you need to find the coordinates of TB1 in basis B. So there is more work to do. And then you need to find coordinates of TB2 in basis B, and so on. So what you have in the representation matrix relative to basis B for inputs and outputs are the coordinates in basis B of the image of each basis vector from basis B. So be careful. Okay? You want outputs in basis B. So when you take TB1, it's not over. This is a vector. Now you need its coordinates in basis B. I need to solve the system and then put them in the first column. You take TB2 and then find coordinates in basis B. Put them in the second column, and so on. So be careful. Again, when you have standard matrix, you have standard coordinates for the inputs, and the result is given in standard coordinates of the output. And we know that vector in standard coordinates is equal to the vector itself. So that's why we write this. So in both of these cases, so this is a standard matrix. So you're multiplying the standard matrix, so standard input, standard output, by the standard coordinates of a vector of inputs, and what you get as output is the image in standard coordinates. Now we know that the standard coordinates of a vector are equal to the vector itself. In this case, I have a representation matrix where the input space, I use basis B, and what I get as output is the standard coordinates for the output space. So I multiply this representation matrix by coordinates of a vector in basis B of the inputs, and what I get as a result is the image, so another vector, right? These are the coordinates of the vector in standard basis, and we know that those coordinates are equal to the vector. So you see the inputs are not the same, but the output in both cases was in standard basis. So that's why we say, okay, here what we get is the vector TV, okay, the object itself. Now it's different when I have a representation matrix where the inputs are in standard basis and outputs are in the coordinates of basis C. So I multiply this representation matrix by coordinates in standard basis of the input, and what I get as a result are the coordinates in the basis C of the output. So I don't get the vector itself, I don't get the image, I get the coordinates of the image in the basis C. So the job is not over. Similarly, if I have representation matrix relative to basis BC, the inputs are given in coordinates of basis B. So I need to find coordinates of a vector in basis B and then do the product here. What I get as a result are the coordinates of the image in basis C. So be careful. Representation matrix works on coordinates. That's what it means. It works on coordinates and gives you, as a result, the coordinates. It's a similar thing here. The only thing is the outputs are given in the standard basis. So the standard basis has some cute property that its coordinates are equal to the coordinates of the vector itself. But if you use any other basis C for the outputs, what you get is the coordinates in basis C of the image. That's what you get. So be careful. So here is the typical problem that we will need to work on. We will have a linear transformation from Rn to Rm, so two finite dimensional spaces. And sometimes we don't even know what's the linear transformation, just to make things nicer. We are given a vector v from Rn, from the input space, and what we want is to know what is t of v. So we want to find the image of v under the action of linear transformation t. But what we are given is a basis for the input space and a basis for the output space. And we are given the representation matrix relative to basis B and C. Okay, basis for the input space B and basis for the output space C. Okay, good luck. Find. So things look a little bit scary, but they are not actually, because we know that this representation matrix relative to bases B and C takes as input the coordinates of a vector V in basis B. That's what it needs to work. And when you do the product, you will get as a result coordinates of the image in basis C. So it gives you as output coordinates of the image in basis C. Finally, this is very nice. It's actually easier and simpler than what we thought. This representation matrix works on coordinates. You need to multiply it by the coordinates of a vector V in basis B. You need to find those and then multiply them, these two guys. You're going to multiply this matrix by those coordinates, and what you're going to get is the coordinates in basis C of the image. Wow, that's cool. We are almost there. So here's the process how we do it actually. So first thing, obviously, we need to find the coordinates of vector V in basis B. So find those coordinates. You need to solve the linear system by Gauss-Jordan. What can you do? Then, once you have those coordinates, you compute the matrix vector product between the representation matrix that works on coordinates and the coordinates of vector V in basis B. So, coordinates of the input in B, okay, coordinates of the input in B. Do the product. What you're gonna get is the coordinates of the image TV in the basis C. Okay, because this works on coordinates, so it multiplies the coordinates of the input in basis B and gives you the as output coordinates in basis C of the image that you're looking for. Okay, so we are almost there. All I need to do, since I have these coordinates of a vector, the image in basis C, all I need to do is apply the definition of coordinates in a basis. What does it mean? That means that TV, the image that I'm looking for, is a linear combination of the basis vectors of basis C, and the coefficients are actually the numbers in this vector of coordinates here, the list. Cool. So it's a linear combination, and the coefficients are just the coordinates in basis C. So it's very simple actually. What you need to remember is that a linear transformation works on objects. So it is defined by its action on basis vectors of the input space, of the domain. Okay? So it takes those objects and gives you objects, in our case vectors most of the time, in the output space W. If we use the standard basis for the output space W, then the representation matrix is simply this. Apply the linear transformation to each basis vector V and put the result in a column of a matrix, and that's how you get the representation matrix relative to basis B for input and standard basis for output. Now, sometimes in some problems, they omit or they don't give you the basis for the input space, for the domain. They don't give you at all. Well, that's not a big deal. Then we assume we are working with the standard basis for the domain. Sometimes, in other examples, they don't give you the basis for the codomain, for the output space. Well, not big deal. Then we work with a standard basis. So, unless the basis is specified, we assume it's standard. If it's specified, well, we need to work with a specified basis. Obviously, we know that for a linear, when we have V and W the same space, one basis works for both spaces. We cannot have any other option. If the basis is specified, that basis is for the inputs and the outputs. So what we learned is that the representation matrix of a linear transformation T is always relative to the basis chosen for the linear space V and W. It always depends on the choice of the linear space, basis for the linear space V and W. And it changes each time we change a basis for V or we change a basis for W. So this representation matrix is really connected to, yes, the linear transformation, but also the basis chosen for the domain and codomain. So when I have a representation matrix here, noted T of B comma C, what this means is that this representation matrix is applied to the coordinates of the inputs in basis B. Okay, I need coordinates in basis B of the domain. And what I get as output when I do the product representation matrix times the coordinates of the object in basis B, I will get the coordinates of the image in basis C. Okay, here. Coordinates of the image in basis C. So that's how we read it. When we see this, that's what it means. TBC means that I multiply this representation matrix by the coordinates of the input in basis B, and what I get is the coordinates in basis C of the output. That's it. So be careful. Read it carefully. Here are some examples that you can solve already for your personal pleasure, and I will solve some examples different from these in a different video. But you can already start working on this material.